So in this lecture, I will present a result on the strong law of large numbers and an application. So I want first to state a theorem. That theorem requires the definition of a function. So let's say that we have a function phi from R to R, which has certain properties. First, I will require phi to be non-negative, so phi of x will be always greater or equal to 0. It will be an even function, so this means that phi of minus x is equal to phi of x. And finally, we will require, if I take a positive x, that phi of x divided by x, it's an increasing function, and that phi of x divided by x squared, it's a decreasing function. So if I call that, say, psi1 of x, so psi1 being phi of x divided by x, what I'm requiring here is that this function psi, it's monotone, which means that psi1 of x will be less or equal than psi1 of y, if x, it's less or equal than y. And if I call that function psi2 of x, so what I'm requiring is that it's a decreasing function. So if I take x less or equal than y, then psi2 of x, it's larger or equal than psi2 of y. So these are the assumptions I'm making here. I'm requiring this function to be increasing and that function to be decreasing in this sense. So let me erase this to continue to state the theorem. Now, assume, so let me state the theorem here. Assume that you have a sequence xj of independent random variables, and assume that we have a sequence an which is increasing to plus infinity, so it's an increasing sequence and it converges to plus infinity. So assume now that the expectation of these random variables are equal to 0, and furthermore assume that the sum for j larger or equal than 1 of the expectation of phi xj divided by aj, phi aj, that this is finite. So phi, it's a function which satisfies these three assumptions. So here I'm requiring that, well, if you take the expectation of phi of xj and you divide that by phi aj, that this is finite. Note that phi it's positive, so this expectation it's always well defined. It could be plus infinity, but here we are imposing it to be finite, and more than that, we are requiring that expectation to be finite. Of course, phi of aj it's a real number, so it can get out from this expectation. And what I claim is that under these three assumptions, then the sum, so x1 of xj divided by aj, these converge almost surely. So if these three assumptions are satisfied, then the sequence of partial sums of xj divided by aj converge almost surely. So this is the theorem which I want to prove. So I just kept the assumptions which I'm going to use. Now xj, it's a sequence of independent random variables. An, it's increasing. They have mean 0. This series is finite. And psi2 defined by this quantity, it's decreasing. So let me start proving the theorem with one claim. So claim 1. So let me define yj to be the random variable xj cutted at the level aj. So this will be equal to xj if xj it's divided by aj, it's less or equal than 1. and it will be 0 otherwise. So I'm cutting xj at the level aj. So if you prefer, you can write this as xj for xj less or equal than aj. And what I want to prove is that the partial sums of yj minus its expectation divided by aj, that this series converge, this sequence converge almost surely. So the expectation of yj is clearly well defined because yj is bounded by aj. And my claim is that this sequence converge almost surely. And for that, we will use the One Series Theorem. So let me define zj as yj minus its expectation. Since the random variables xj are independent, the random variables yj are independent, and therefore zj is a sequence of independent random variables. So this is the first assumption of the One Series Theorem. Then, by definition, the expectation of zj is equal to 0. By definition, so this is the second assumption. And therefore, what I need to check in order to guarantee that zj divided by aj converge is that the sum of the expectation of zj divided by aj square, that this is finite. Right? So I'm applying the One Series Theorem to the sequence zj divided by aj. Of course, these sequence it's independent, its expectation is equal to 0. So if I can prove that this series it's finite, I will get that the sequence zj divided by aj, j from 1 up to n, converge almost surely. And this is exactly what I'm claiming here. So in order to prove that, I only need to check that this series is finite. So let's do that. So the expectation, so this is equal. So let me write this sum. I have a sum, 1 over aj square. And now expectation of zj square, but the expectation, by definition, zj, it's yj minus the expectation of yj and its square. So this is the variance of yj. Well, the variance of yj, it's bounded by the second moment. So I have here 1 over aj square, the expectation of yj square. So this is the variance, it's bounded by the second moment. Now let's recall what is yj. So this is equal to the sum. For j larger 1, I have 1 over aj square. And now yj, it's xj, provided that xj is bounded by aj. So this is xj square on the set at which xj it's less or equal than aj. And now I have xj here divided by aj square. So now let's use this. So let me erase the definition of z. And what I know is that psi2, it's a decreasing function. This means that if x it's less or equal than y, then psi2 of x, well, and let me write psi2 as phi of x divided by x square, that this is larger or equal than phi of y divided by y squared. And so now I know that xj, it's bounded by aj, so I will use that with xj less or equal than the modulus of xj less or equal than aj. So this tells me that, well, by this inequality, I have that phi xj divided by xj squared, it's larger or equal than phi of aj divided by aj squared. And I will rewrite this inequality as phi of xj. So I'll divide by phi of aj. And I will multiply by xj squared. And here I note that I'm using that xj, that phi, it's even, to replace phi of modulus of xj by phi of xj. So I used here the fact that, so remember this inequality hold if I took x and y non-negative. So here I'm using the fact that phi, it's even. Sorry for this interruption. So now let's go back here. I have this inequality. So I'm multiplying by, I'm dividing by phi of aj, and I'm multiplying by xj squared. So what I get is that xj squared divided by aj squared, it's bounded by phi of xj divided by phi of fj. So in the set in which xj it's bounded by aj, I can replace the ratio xj squared divided by aj squared by phi of xj divided by phi of aj. So this is bounded by the expectation of phi of xj, phi of aj, xj less or equal than aj. But now phi, it's non-negative, and this is bounded by 1. So this is bounded finally by the sum for j larger than 1 of the expectation of phi of xj divided by phi of aj. And by assumption, this sum, it's finite, and therefore this proves that indeed the sum is finite, and therefore that the sum, the partial sums of szj divided by aj converge. And this is exactly what we wanted to prove. So this completes the proof of the first claim, which was that the sequence yj minus expectation of yj divided by aj was converging almost surely. So here are the assumptions. Now what we are going to use in this part of the proof is that the function psi1 defined by phi of x divided by x, it's increasing if x is positive on R plus. And we already proved in the first claim that if I define yj by this formula, so this is a concise way in which to express yj, then we know already that yj, that this sequence converge almost surely. Now, my second claim is to show that the sums of from 1 up to n of the expectation of yj divided by aj, so that this sequence converge. So this is a sequence of real numbers, and what I'm claiming is that this sequence is converge. Once we proved claim 1 and claim 2, it follows from claim 1 that actually yj divided by aj converge almost surely. So now we are going to prove this, this statement. So yj, by definition, is the expectation of xj on the set in which xj it's less or equal than aj. And what we're going to do in order to prove that this sequence is finite is to show that this sequence converge. It's to prove that if I take the absolute value here inside this sum, that this is finite. So it's clear that if we prove that this series is absolutely convergent, then the partial sums converge. And so what I'm putting here, it's an absolute value mined outside of the expectation. And here we were going to use the fact that xj has mean 0. Since xj has mean 0, I can divide this expectation as the expectation of xj times the indicator that xj is less or equal than aj, plus the expectation of xj on the set at which xj is larger than aj. And it follows from the fact that this expectation is equal to 0, that this sum is equal to 0, and therefore that this expectation in absolute value is equal to that expectation in absolute value. So here, since I place this absolute value, I can replace the inequality xj less or equal than aj by the inequality xj larger than aj. And once I replace this inequality by greater than, I will place the absolute value inside the sum to say that this is bounded by the sum from 1 to n of 1 of aj, the expectation of the modulus of xj, times the characteristic function on the set that xj is larger than aj. And we want to show that this sum is finite. So now we are going to use the fact that psi1 is monotone. So remember that psi1 monotone means that if I take x less or equal than y, then phi of x divided by x, it's less or equal than phi of y divided by y, provided x and y are non-negative. So I want to apply this inequality for aj and xj. So I'll take x to be aj, y to be xj. So since aj it's less than xj, by this inequality, I have that phi of aj divided by aj, it's less or equal than phi of the modulus of xj divided by the modulus of xj. Now phi is even, so I can remove the absolute value inside of phi and get this inequality. Now let me multiply this inequality by xj and divide it by phi of fj to get that xj divided by aj, it's bounded by phi of xj divided by phi of aj. And therefore, I can replace xj divided by aj by phi xj divided by phi fj. So this expression, this sum, it's less or equal, so let me write it here, less or equal than the sum from 1 to n of the expectation phi of xj divided by phi of aj. Again, I have this indicator function, but since phi is a non-negative function, it's a positive function, I can bound this characteristic function of a set by 1 to say that this is bounded by, I said characteristic, but I wanted to say indicator function, the indicator function by 1 to say that this sum is bounded by that one. And now, by assumption, I can take n to infinity, and this is bounded. So that proves the second claim. The second claim was saying that, well, this sequence, it's converging, and therefore, well, this sequence without the absolute value, it's converging, and therefore putting together these two claims, what I have up to now proved is that the sum from 1 to n of yj divided by aj converge almost surely. Now, up to now, we have from claim 1 and 2 that if I define yj by this formula, then this sequence, it's converging almost surely. Now, claim 3, in order to complete the proof, what I need to show is that the probability that, so this is third claim, the probability that xj is different from yj infinitely many times, infinitely often, that this probability is equal to 0. Right? If I can prove this claim, since they are different infinitely many times with probability 0 and a set of probability 1, they are equal starting from an index, and therefore if this sequence converge, the same sequence with xj instead of yj also converge, and this was the statement of the theorem. So in order to complete the proof of the theorem, it remains to show that this event has probability 0. We know by Borel-Cantelli that in order to prove that, it's enough to show that the sum of xj different from yj, it's summable. You can show that this sum, this series, it's finite, then we know by Borel-Cantelli that the probability of this event is 0. But xj different from yj means that, by definition of yj, that xj is in absolute value larger than aj. So this is, by definition of yj, this event corresponds to the event that xj it's larger than aj. Now, I claim that phi of x, it's increasing on R+. In the sense that if I take x less or equal than y, then phi of x, it's less or equal than phi of y. And let me, well, this is because if phi of x divided by x, it's increasing, phi of x has to be increasing. So let's prove that. So let's take x less or equal than y. And let me write phi of x as well. I will multiply that by, so I'm taking positive numbers, let phi of x. I'll multiply this expression by x and divide it by x. Now x, it's positive, and phi of x divided by x, which is psi1, it's increasing. So this is bounded by x divided by phi of y divided by y. Because psi1, it's increasing. And now, well, x divided by y, because x, it's bounded by y. This is bounded by 1. And phi, it's positive, so this is bounded by phi of y. And this proves, therefore, that indeed phi, it's an increasing function. Right? So if this is true, I can here apply phi. If xj is larger than aj, then phi of xj is larger than aj, which means that this sum, it's bounded by the sum for j larger or equal than 1 of the probability that phi of xj it's larger than phi of aj. Phi, it's even, so I can remove the absolute value here, and what I get is this expression. Now I can apply Chebyshev inequality to say that this is bounded by the sum of 1 over phi of aj, the expectation of phi of xj. And by assumption, this is finite. So this proves that indeed this sum is finite, and therefore that xj is different from yj infinitely often with probability 0, and that completes the proof of the theorem. So here is the theorem we just proved. We have a family of independent random variables. They have mean 0. we take a sequence aj which is increasing to infinity. Phi, it's an even function which is such that phi of x divided by x it's increasing, phi of x divided by x squared is decreasing, and we assume that this sum it's finite, then what we get is that this sequence converge almost surely. So I wrote this theorem just to extract from it some results. First, there is a corollary which follows from the a lemma, which is called the Kronecker lemma, which I already stated here. We get immediately from Kronecker's lemma and this result that under this assumption, x1 plus xn divided by n, that this is converge almost surely to 0. Okay, so we have a strong law of large numbers under these assumptions. Now, of course, all the question is to get phi, to find phi, and the examples are obvious. Or the first example is obvious. Take phi of x to be equal to x to the power p for p between 1 and 2. So let's check that the assumptions are satisfied. It's indeed a non-negative function. It is even. If you divide that by x, you get p minus 1. And therefore, x, since I take p larger or equal than 1, this is indeed an increasing function. If I divide that by 2, since I take a p less or equal than 2, this is p minus 2, and therefore it's a decreasing function. So indeed, these assumptions are satisfied. And therefore, it follows from this theorem that if I have a sequence xj of independent random variables with mean 0, and if the expectation, so if I have a sequence aj which is increasing to plus infinity, and if we know that the sum for j larger than 1 of x to the power p, or j to the power p, I'm sorry, and expectation of xj, and this is aj, if this is finite, so if the sum of the expectation, the absolute value of xj to the power p, it's a fixed number between 1 and 2, a real number between 1 and 2, and this divided by aj to the power p, so let me get it right, this is aj to the power p. If this is finite, then the sum of xj divided by aj from 1 to n, this converge almost surely, and x1 plus xn divided by an converge to 0 almost surely. So this is immediate consequence of the previous result. And here, mind that I'm not dividing that by n, but dividing that by an, right? So this is this was Kronecker's lemma. Okay, and so we get that now we have a concrete example. If you want to prove that x1 plus xn divided by an converge almost surely to 0, well, if your random variables have mean 0, what you need to check is that this sequence, this sum, it's finite for some p between 1 and 2. Another example or application of this theorem is assume that the expectation, you can bound the expectation of xj to the power p by some constant m. So assume that there exists a p between now strictly 1 bounded p and 2. So assume that you have a p between 1 and 2, and m, finite real number m, such that this expectation is bounded by m for all j. Now you take, let me take aj to be just j. And in this equation, in this theorem, phi of x to be x to the power p. So we already checked that phi x equal to the absolute value of x to the power p indeed satisfies all this assumption. So what we need to check in order to apply this theorem is that the expectation of phi of x, which is x j to the power p, divided by j to the power p, sum from j from 1 up to infinity, that this is finite. But since the expectation, so if this is true, what we get is that the sum of xj divided by j from 1 to n converge almost surely, and also that x1 plus xn divided by n, that this converges to 0 almost surely. Right? So if you're able to prove this inequality, we get these two results. But since we are assuming that the expectation of xj to the power p is bounded by some constant m, so this is bounded by m times the sum for j larger or equal than 1 of j to the power p. And since we assumed p to be strictly larger than 1, this is finite. So indeed, if we have that xj, it's a sequence of independent random variables and which have mean 0, and if moreover we are able to bound uniformly in j the expectation of the absolute value of xj to the power p for a p larger than 1, then we have immediately that xj divided by j converge, that these sums converge, and that the average of x converge to 0, and this almost surely. So here's, well, another application of this theorem, which means that if you have these two conditions together with these third conditions, then these two results hold. So let me give you a last example. And now I will assume that the sequence xj, it's IID. So up to now we assumed only independence, but now I'm also assuming that they are identically distributed and that they have a finite second moment. So let me represent by square the expectation of as x1 square, and let me assume that this is finite. Now let me take a special sequence an. So an will be, well, a1 will be any real number, strictly positive, and then for n larger or equal than 2, I will define an as 1 over, n square root of n times the logarithm of n to the power 1/2 plus epsilon. So this is my sequence an. And as phi, I'm going to use phi of x, it's equal to x squared. So I've already seen that phi of x satisfies all these conditions. And so what I need to check is that if this condition is satisfied in order to guarantee that this expression converge and that x1 plus xn divided by an converge to 0 almost surely. So, well, we have that indeed this sequence is dependent. They have mean 0 by assumption. And now let's check that this sum is finite. So this is the sum for j larger than 1 of 1 over phi a, but phi it's square. So what we get here it's an square. So I won't care about a1 because a1 is fixed. So this is j log of j to the power 1 plus 2 epsilon. And now I have the expectation of phi of xj, phi of x squared, so the expectation of xj squared. And of course here I'm taking epsilon strictly positive, right? I'm taking epsilon, any strictly positive real number. And so this is equal to, well, xj, they are identically distributed, so this expectation, it's just sigma squared. I said that a1 I fixed anything, so I have one a1 square, and then plus the sum for j larger than 2 of this quantity, and this is j times log of j to the power 1 plus 2 epsilon. And I leave it to you. So here there is a slight abuse of notation because the definition of a1 is not this one, but that's okay. Oh, it's clear that you understand that here for j equal to 1, I mean a1 squared. So it's what I wrote here. And well, I leave to you to check that this sum, it's finite, and therefore that indeed this is finite. Therefore, we can apply the theorem, and the theorem tells us that xj divided by aj is this number, converge to 0, and what's more interesting is that we get that x1 plus xn divided by an. So now let me write what an is. An, it's square root of n times log of n to the power 1/2 plus epsilon. So what we proved, it's something stronger than the law of large numbers. Of course, we had here an extra condition because we are imposing the second moment to be finite. So if the first moment it's 0 and the second moment it's finite for a sequence of IID, the law of large number would say that x1 plus xn divided by n converge almost surely to 0. And what we just proved is that, well, something substantially stronger, that you don't need to divide it by n to have a convergence to 0 almost surely, but it's enough to divide it by square root of n times log n to the power 1/2 plus a strictly positive epsilon. And we will see, well, that this is the best result because if we take epsilon equal to 0, then it's not true anymore that you're converging to 0. So we'll see that later in these lectures, that if you remove this epsilon, then it's no longer true that you converge to 0. But so that's a pretty interesting result, that if you take the sum of the first n terms and you divide only by square root of n times log n to the power slightly larger than 1/2, then you still converge to 0, provided that the random variables have a finite second moment. Now let me give you an application of this strong law of large numbers. You'll see throughout these lectures many applications of this result. Let me start with one simple application. So I'm fixing f, a distribution function. So remember, it's a function which is right continuous. It converges to at plus infinity to 1, at minus infinity to 0, and it's monotone. So f, it's a distribution function. It's a distribution function of certain random variable x. Now we will take x1, x2, and so on, IID random variables. And I will assume that these random variables have the same distribution, so that f, it's equal to fx1. you can, for instance, one example here, maybe to fix idea, will be to take f, the distribution function of the uniform in 0, 1. So you know that the distribution function of the uniform, it's equal to 1 starting from 1. It's 0, and then it's linear between 0 and 1. So that will be, so this is 1, this is 0, 0, and this is our distribution function f. And now you take x1, x2, random variables which are independent and have uniform distribution in the interval 0, 1. So what you get when you do this is that, well, x1 will be a point between 0 and 1, x2 will be another point, x3, x4, and so after n steps, you have n points in the interval 0, 1. And more generally, if you take any distribution, what you'll have is n points in R. Now, what I want is to approximate this distribution function by these results. So what we will do is, let's take, let's call x, maybe y1 the smallest point, y2 the second smallest. So we have x1, x2 up to xn. Assume that you fixed an omega, so you have x1, x2 of omega, xn of omega. And what I want to do is I want to construct a distribution function, fn of omega, which is the one I obtain from the points x1, x2 up to xn. So what you would do, you have here four points. So what I will do is to divide this interval 0, 1 in 4 intervals. And the natural approximation of the distribution function will be to define this function, which is 0 until you hit the first random variable, so the smallest one. It's right continuous, so starting at this point, you declare it to be equal to 1/4 until you find the second point. At this point, it's right continuous, so from that point on, you declare it to be equal to 1/2. You follow until you reach the third point. Third point, it's 3/4 till last point, and starting from the last point, you get 1. So that would define this function fn, which depends, of course, on omega. If you have a different omega, you'll have different points, and therefore a different function fn omega. So I did that for 4 points. Now you can imagine that you did that with n points. I will define what I mean by fn. But before I want to state the theorem which I want to prove, what I want to prove is that the function, the distribution function obtained in this way, converge to f uniformly in R. So this convergence is uniform in R, and this almost surely. Which means that what we will do is we will construct a set omega 0, which has probability 1. And we will prove that for all omega in this set, fn omega defined in this way, so in this informal way which I presented, converge to the distribution function f uniformly over R. So this is what I plan to do in this last part of the lecture. So let's recall, f is a distribution function of a certain random variable x, and I'm assuming that in some probability space, omega fp, I have a sequence of IID random variables xj, whose distribution function is equal to the one given. Now, step 1, I want, so given x1 of omega, xn of omega, construct a function fn of omega, which approximate my function f. So let me draw again here the points to explain what is the idea. So I want to define Fn of omega at x. So what is the definition? You have a point x here. You want to compute the value of Fn at the point x. Well, the value will be given by the number of points which is on the left of the point x divided by n. So Fn of x will be equal to 1 over n. So n, it's the number of points you're using. It goes from 1 to capital N. So I'm dividing this by 1 over n. And then I'm counting the number of points which are on the left of x. So this is the indicator function of the set that xj of omega, it's less or equal than x. So I'm counting the number of points xj which lie at the left of x. I'm dividing this number of points by n, and this is the definition of my function fn. See that fn, it's clearly a distribution function for all omega, because, well, if I fix an omega, I have these n points. To the right of the last point, by definition, fn is equal to 1. To the left of the first point, fn is equal to 0. Fn, it's clearly increasing, and it's right continuous because here we are taking less or equal. So this is our formal definition of fn. And my first claim is that if I fix x in R, then Fn of omega x converge to Fx almost surely. So I'm fixing any point x in R. I'm looking the value of this distribution function at x, and I'm claiming that it converges to Fx almost surely. So let's prove that. Well, let me call yj this random variable. So yj will be equal to the indicator function of the set xj less or equal than x. So yj, since the xj are IID, yj, it's a sequence of IID random variables. And the expectation of yj, it's equal to the expectation of the indicator function, the indicator of the set xj is less or equal than x. This is equal to the probability that xj is less or equal than x, and this is f of x. And moreover, well, yj, it's absolutely bounded, so the absolute value of yj, it's bounded by 1. So what we get is that by the strong law of large numbers, y1 plus yn divided by n, that this converge almost surely to the expectation of y, but this is fx. What is y1 plus yn divided by n? Well, this is exactly fn. So fn of omega x, it's exactly the average of 1 over n y1 plus yn. Right? You see that yj, it's the indicator of the set xj less or equal than x, and this is exactly the definition of fn, and therefore by the law of large number, this is indeed converging to f of x almost surely. So we proved our first claim. So we know that for all x, these converge almost surely. So let me consider a set D, which is contained in R, and I will assume that this set is dense and countable. So for x in D, so let me take, since D it's countable, let's represent by xj, maybe zj, j larger than 1, an enumeration of that set. And if I fix some zj in the set D, I know that fn of zj converges to fzj almost surely. So this means that there exists a set omega zj, which belongs to the sigma algebra F. P of omega zj has probability 1. And if omega belongs to omega zj, fn of omega zj converge to f of zj. So this happens, this holds for all omega in this set, which has probability 1. So now let me call omega d the intersection of all zj's, omega zj. Again, since every set omega zj has probability 1, this means that the probability of omega d is 1. And now if I take omega, if I take a point omega in the set omega d, which has probability 1, what I get is that fn of omega z converge to f of z for all z in D. Right? So fn of omega z converge to f of z for all z in D. So this implies that fn converge to f. So we have seen that in the exercise, that this implies that fn converge vaguely to f, vaguely or weakly to the function f. So we proved already that fn, this sequence, so that there is a set, omega d, which has probability 1. And if I take any point omega in this set, omega d, then fn of the function fn, which depends on omega, but this function fn converge to f weakly in the weak sense that we introduced before. But what we want to prove, and this is our next step, is that actually this convergence, it's not weak, it's strong. It's uniform over R. So up to now we proved that for a set of probability 1, we have weak convergence. Now we claim that actually we have strong convergence. So up to now we defined this function fn, which I'm calling the empirical distribution function, because its value depends on these random variables xj, the values of these random variables. So in this sense, it's empirical. And so we defined that function. We fixed a dense and countable subset of R, and we proved the existence of a set which is measurable, which has probability equal to 1. And for all omega in this set, fn omega at z converge to fz for all points z in D, in this countable dense subset. Now, so we've seen that this implies weak convergence. Now we want to show that actually we have strong convergence. So let me define by E the points at which f is discontinuous. So these are all the points x in R, such that f of x, f has a jump at x, so its value at x, it's different from the value, the limit at the left of x. So remember, fx minus is the limit as y increase to x of f of y. So it's the left limit of the function f at the point x. And saying, since f is right continuous, saying that it has a jump or it's discontinuous, it's saying that its value at x is different from its left limit, which is represented by fx minus. Now we know that E, it's a countable set. there is at most a countable number of jumps. Fine. So since E is a countable set, let me write E as, let me give a enumeration of E. So E will be represented by yk for k larger or equal than 1. And now let me fix k, and I will define y at omega k to be equal to the number of points which are equal to yk. So yk are the points at which the distribution function has a jump, which means that there is a mass, so that the measure of x is positive. Since the measure at x is positive, well, certain of these random variables will take that value. So this is the number of the random variables before n which take that value. So this is the sum from 1 to n, and I will sum if xk, xj of omega it's equal to yk. Right, so I'm fixing again, I'm fixing k, so I'm fixing a point yk in these sets at which there is a jump, and I'm counting from 1 to n the number of xj which are equal to yk. And I'm dividing that by that, and this is my definition of hn yk, omega k. So again, this, I can represent that by a sum of random variables yj, wj. So let's call wj this indicator. So wj it's either 0 or 1. It's 1 if xj is equal to yk. It is 0 otherwise. And the expectation, yj are I, wj are iid, random variables. The expectation of wj, it's equal to the expectation of this characteristic of this indicator function. The expectation is equal to this probability, and the probability it's independent of j because they are identically distributed. So it's the probability that x1 is equal to yk. And the probability that x1 is equal to yk, it's the jump at yk. So this is f of x1 yk minus f of x1 at yk. But the distribution function of x1, it's f. So this is f of yk minus f of yk minus, of course. So this is the expectation of yj, wj. So wj, it's a sequence of IID random variables. This expectation is given by that. So the law of large numbers tells us that w1 plus wn divided by n converge to the expectation of w1, but this is f of yk minus f of yk minus. And w1 minus wn divided by n, it's exactly hn. Okay. So this is showing that hn k, it's converging almost surely to fyk minus fyk minus. So what we proved is that for all k, hn omega k, which is defined by this expression, it's converging almost surely to fyk minus fyk minus. So this is what I'm going to write here, saying that hn k converge almost surely to fyk minus fyk minus. Well, and what is now mind? That this is exactly equal to fn omega. So let me put an omega here. this is fn omega xk minus fn omega xk minus. Right? So if you remember the definition, this is the sum of of points xj which are less or equal. So there is a problem here of notations. This is, sorry, yk. There was a problem of notation. This is yk minus. And by definition, this is the number of j's from 1 to n, divide that by n, which are less than yk. And this function, well, it's constant. So if you remember the definition, here's yk. Here's my definition of fn. Fn, this jump here corresponds to the number of points, this distance, so which is fnyk minus fnyk minus, corresponds to the number of points whose values are exactly equal to yk. So, and this is what we called hn. So hn, it's exactly this difference, right? So I hope you're convinced that fn of omega yk, and what I was saying is that to the left of yk, this function is constant up to 1 point, up to the first jump of this function. So fn, it's constant by intervals, so these numbers, well, the limit, this difference minus this point is the number of points, and this is exactly the left limit. So this shows that indeed hn omega k is equal to that difference. So what we proved is that for all yk, up to now, for all yk, this difference is converging almost surely to this difference. So what does that mean? That means that there exists a set lambda k, which belongs to the sigma algebra, which has probability 1, and for all omega in lambda k, fn of omega yk minus fn omega yk minus, this is converging to fyk minus fyk minus. So this holds for all omega in omega lambda k, and lambda k is a set of probability 1. So now if I call lambda the intersection for k larger than 1 of lambda k, I still have that the probability of lambda is equal to 1, because each of the sets lambda k has probability 1. And now for all omega in this set lambda, which has probability 1, I have that this limit holds for all k. So we have that fn omega yk minus fn omega yk minus converge to fyk minus fyk minus. And we are almost there, because now what we will do is we'll take the intersection of omega and lambda d. So let me call to unify the notation this set lambda, let me call it omega e. So E, it's the set of discontinuity points of F, and let me represent this set lambda by lambda E. So what did we prove so far? We proved the following. let me take now omega 0 as omega d intersection omega e. So the probability of omega 0 is 1. And what we know is that for all omega in omega 0, we have these two convergences. So we have that Fn is converging to F for all points in D, and that the difference is converging to the difference. So for all omega in omega 0, we have that Fn omega z minus, it's converging, sorry, to Fz for all z in this dense and countable subset D, and Fn of omega yk minus Fn of omega yk minus, it's converging to F of yk minus F yk minus. So this is what we proved. So let me read it again. We proved that there exists a set which has probability 1. And for all omega in this set, we have two convergences. First, Fn of omega at z converge to F at z for all z in this point D, which is a dense subset, for all points z in D, which is a dense countable subset of R. And for all discontinuity points of F, the jump at yk at the discontinuity point of Fn, it's converging to the jump at yk at the discontinuity point of F. And what I claim is that if these two conditions hold, then Fn omega as a function in R, it's converging uniformly to F, uniformly in R. So I leave it to you to check this last step. What I'm claiming is that if you have a function, a sequence of distribution functions Fn, which has these two properties. First, that for a dense countable subset, you have pointwise convergence. And for all discontinuity points of F, you have convergence of the jumps. Then actually you have uniform convergence. So I leave it to you to prove this last part of this application as an exercise. And once you do that, you conclude that indeed you have uniform convergence, almost sure uniform convergence of the empirical distribution to the distribution. So you have a set which has probability 1, and for all omega in this set, the empirical distribution is converging to the distribution uniformly in R, which is quite a strong result. So with that, I complete this lecture.